In this class, we're going to see one of the most interesting, fun, useful, powerful tools related to matrices. No surprise, I'm talking about determinants, right? But what are these determinants? Well, first of all, I have to tell you that despite all the good things I've just said about determinants, there is one bad thing to say about them, and that is that the theory behind determinants is awfully complicated, not so much in terms of complication of ideas, but in terms of computations of checks, of proofs. Many of the things I'll be telling you can be proved fairly easily, but through some methods which are pretty boring, especially if we try to do them in great generality. So in this class, I'm going to try to stick to the main concepts, the main ideas that I want you to understand, absorb, and implement. I will refer you to the textbook as well as to my notes in terms of some of the technical details and see how they're developed there. And incidentally, in my own notes, as well as in the textbook, you're going to see a different approach from what I'm going to show you in these notes. In this video, and that's done on purpose so as to give you different approaches to something which again is very, very important, so you need to see it from different points of view, but also it over the years is something that has changed quite a bit, has taken different lives of its own, and so it needs to be looked at in different ways. So let's see, first of all, what is it that we're trying to accomplish? We're trying to actually address a fairly general mathematical problem, one that you're going to see, actually one that you've already seen in many situations, although perhaps it has not been presented to you that way, and that you're going to see again. What is the problem? The problem is to associate to some kind of complex mathematical object A, which I'm representing here by eggs, flour, and sugar, so something fairly complicated consisting of several things or with a fairly complex structure, and associate to it a single number, C. Okay? But not arbitrarily, of course, not in some useless way just for the fun of it, but in some way that provides useful information about A. So it's sort of taking all these complicated things and making it into a nice tasting cake. This is again something that you have seen before and you'll see it again. Here are some examples of where you have seen this problem in action. For instance, for a vector, we have seen how to compute its length. What do we do with the length of a vector? We take something complex, namely a vector, and we change it to a single scalar, namely its length. Also, for two vectors, we have been computing their dot product. So what we have here is a set of two vectors, each of which has a fairly complex structure, and we're changing that into, or putting them together and coming up with a single number out of it. In other contexts, you may remember computing the mean of a set of data, right? So what you do is you take a whole bunch of numbers and you summarize them into this single number called the mean. So this is again something that you have seen before. You will see it again. Let's see how that applies to square matrices. Before I explain to you how we're going to summarize a square matrix into a determinant, I have to make again a few preliminary explanations just to lay the groundwork and explain to you why I'm going to do certain things the way I am. First of all, there is a traditional way to define the determinant of a matrix that we will be seeing shortly, or we'll have a glimpse of it shortly. Okay, that's the historical way, the way it was originally done, but it's very long, very complicated. It involves a lot of operations. It involves a lot of formula which are very complex in their structure and so on. So we're going to try and avoid that. Okay. Instead, we're going to use a more intuitive method, which is based on things that should be fairly familiar to you. Well, first of all, I'm going to actually use the traditional method for 2x2 matrices. For 2x2 matrices, that's a very simple case that can be explained very, very quickly, very easily. And the idea that we're going to see there and we're going to develop there is going to then be used in order to develop the definition of determinant for bigger matrices. And then we're going to use some properties related to elementary operations and elementary matrices. We have studied those recently. You may remember the fact that each elementary row operation corresponds to multiplication by an elementary matrix. And so we're going to use those elementary matrices and the corresponding row operations quite a bit. And then we're going to use quite heavily one of the properties of determinants, namely that they preserve the product of two matrices. What do I mean by that? It means that computing the determinant of a matrix, of the product of two matrices is going to be the same as computing the determinants of the two matrices separately and then multiplying them together. So this is sort of an associative kind of a property that we can look into. This is in fact one of the main properties of the determinant, and we want to make sure that we keep it. So what we're going to do is we're going to use this property to define the determinant of a matrix. Okay? So what we're going to do is we're going to define in this way something, which again, no surprise, is going to be called the determinant of A, and is denoted in the same way that we denote absolute values. However, don't be confused. This is not the absolute value. It's just the same notation with a different meaning. In fact, the determinant of a matrix can very well be negative, and those two bars don't make it positive. So keep that in mind. That symbol in the context of matrices does not mean absolute value. It means something quite different. All right, so let me explain to you now how this is done.